Right. So last time we looked at the probability of sequential events where the first event did not affect subsequent events, like flipping a coin. You flip a coin once, that doesn't change the coin. It's going to have the same probability of heads or tails on the next flip. Same thing with dice. What about a deck of cards? If you draw a card from a deck, you've changed the deck. So the probability of subsequent events is going to be affected by that. We call those dependent events because the probability of subsequent ones depends on what happened on the first ones. So let's talk about that a little bit. We're going to draw two cards, and then we're going to draw four. But all these examples are, suppose we're going to draw two cards from a deck. What's the probability that they're both going to be hearts? Well, let's go back to multiplying the probability for the first draw times the probability for the second draw, like we did with coins, 1/2 times 1/2 times 1/2. The probability of drawing a heart on the first draw is 10 out of 40, because there are 40 cards in the deck and 10 of them are hearts. But the second draw has now changed because the deck isn't the same as it was before. We're not putting that first card back. So how many cards remain in the deck? Well, if you started at 40 and you took one out, there's going to be 39. And how many of those are hearts? Well, if the first one was a heart, that's what we're counting on here, the first one's a heart and then the second one's a heart, that means there are going to be only 9 hearts left in the deck. So our probability of drawing 2 hearts, or that both of the 2 cards we draw, is going to be 10 times 9 over 40 times 39, which is about 0.058, just a little bit less than 6% of the time. And yes, I've cheated. I didn't want to stand here and punch keys on a calculator in front of you, so I pre-ran these numbers. I do want these decimal approximations here because I want you to be able to check your intuition. If you're drawing 2 cards out of a deck and 10 out of the 40 cards, again, we're using our limited deck, are hearts, then how unlikely would it be? Remember, probability is the study of likelihood. How likely would it be for them both to be hearts? Well, not hugely likely, but it's not going to blow your socks off if they are. So we're looking for something that's a fairly small probability, but not too tiny. And 4.8% or 5.8% to me fits that description. Now, think about this here. Probability of 2 or both of the 2 cards being aces. We're going back to our full deck. We'll put back the hearts that we drew last time. If we want them both to be aces, the probability is going to be, on the first draw, there's 40 cards in the deck, and only 4 of them are aces. So here we get 4 out of 40. And if we draw an ace on the first draw, the probability on the second draw that we get another ace is the remaining 3 aces out of the remaining 39 cards. Now, obviously, the denominators are the same, and that's going to be the same anytime we draw 2 cards, right? We're going to start with 40 on the first draw, and then there'll be 39 left on the second. So our denominators are going to stay the same for all of these. The numerators will change, and the rarer the card is in the deck, the less likely it's going to be to show up, right? We have 10 hearts in the deck, but only 4 aces. So the likelihood of getting a pair of aces should be much smaller than a pair of hearts, and it is. It ends up being 0.0077, which is less than 1%. Okay, how about probability of a heart and then a diamond? Well, on the first draw, 10 hearts out of 40 cards. But this time we're not drawing another heart. We're going to draw a diamond on the second one, and the probability of that is the number of diamonds remaining divided by the number of cards. So of the 39 remaining cards, 10 of them are still diamonds, which is slightly better than this, right? We got 2 10s up top instead of a 10 and a 9, and that does end up being 0.064. So about 6% of the time, you'll get a heart then a diamond. How about an ace then a 10, right? Similar to 2 aces, except not the same. Probability of drawing an ace on the first one is going to be 4 out of 40. And the probability of a 10 on the second one, there's 39 left in the deck, and all 10s remain. And that's going to give us about 0.01, which is a little bit bigger than this, right? This is 0.7%, 0.7 of 1%. This is 1%. Okay. Little notation I want to touch on here. If you go to another source for this information, which I don't mind at all if you do, but you're going to run into this notation here, which means the probability of A given B, meaning the probability of this happening given that that's already happened. I'm not going to hold you accountable for that notation, but that's what we're talking about here. What's the probability of drawing an ace on the second card given that you already drew an ace on the first? So the deck's going to be smaller, the number of aces is going to be smaller. That's what this notation is talking about. So don't let that notation scare you. It's very simple. It's something you know how to do. We're just not bothering with the notation. Couple more. What's the probability of drawing a pair? Any pair. If we're talking about a pair, it doesn't matter what the first card is as long as the second card matches it. So the probability of the first card being a card is going to be 40 out of 40. And what's the probability the second card's going to match it? And we're talking about pair, we talk about matching faces. So same number, not same suit. Well, there are 39 left in the deck. That's not going to change. And how many of them will have the same face as the first? Well, we already drew one with that face. So it's going to be one less than that, or one less than there were when we started. So it's going to be 3 out of 39. That's 1 in 13, or about 0.077. So about 8% of the time, if you draw two cards, they're going to be a pair. Seems pretty reasonable to me. Now let's look at a couple, not wackier ones, but let's suppose we draw 4 cards. What's the probability that all 4 of them will be hearts? Well, there are 10 out of 40 for the first draw, and then 9 out of 39, and then 8 out of 38, and then 7 out of 37. Right? Each time you draw a card, the deck gets smaller by 1, and also the number of hearts remaining, if we're drawing all hearts, is going to get smaller as well. And that comes out to be about 0.2% of the time, which isn't surprising. You draw 4 cards out of a deck to get a flush, all matching suit, is an unusual thing. What about to get all 4 of them being aces? Remember, the denominator is going to stay the same. It's going to be 40, 39, 38, and 37, because the deck is shrinking by 1 each time. But we start out with 4 aces, then there's only 3, then there's only 2, and then there's only 1. And that's going to happen about I've got it written here, 0.00001, which is 1/10,000th of the time. So if you deal out of our limited deck here, you can expect to get all 4 aces about 1/10,000th of the time. Give that a shot. Do it 10,000 times, and I predict that about one of those times you get all 4 aces. Good luck.